the information content. If you tell me what the treatment was, that'll tell me how to do a Bayesian update about how much I should believe you're going to get a peanut allergy. And they add up. If you apply several different treatments that have log odds ratios of 1, 2, and 3, the total of all of those treatments is 6. At least if I assume that they're independent. Yes? Shoot. The problem with log odds ratios is that nobody knows what they are huge, but nobody knows what they are. You have 2 axolotls. How many other people knew what an axolotl was? All right, they're not quite as obscure. How many people knew about log odds ratios? They're exactly the same. So my analogy is apt. They are, and they're very cute. Although I always get confused with an atlatl, which I guess is not good. That's the spear throwing thing. Oh, interesting. Interesting. This is great. We might be off topic, but this is really good. I have only myself to blame. To summarize, there are a lot of different ways to express this. None of them are perfect. There's a little bit of a trade-off here from left to right. The things on the left are problematic from a mathematical point of view, but people understand them. The things on the right are in some sense elegant and mathematical and all that, but for a popular audience, you're not going to get people to understand that. And that's the trade-off that I'm suggesting, is to express effect size, there's probably not one ideal way to do it. You want to choose something that is meaningful in context. You want to choose something that makes sense to your audience, but there's a conflict there. See? I suggest we take a break. Let's resume in 10 minutes, which will be 2:40. If you have questions for me, I'm happy to talk during the break. Hey, we should reconvene if everyone's back from the break. I got one question. Actually, several people during the break were asking about this odds ratio and log odds ratio. I was singing their praises about how wonderful they are mathematically, and people were asking, how do I make sense of them? What is my intuition for those things? I will point out, I won't get into this in any depth, but the log odds ratio is the Bayes factor. So if you are familiar with Bayesian statistics, or a Bayesian update using Bayes' rule, the Bayes factor is a measure of the information content. And if you look up the Wikipedia page for Bayes factor, it actually has a table here that was suggested by Jeffreys. Now, you don't have to take this as gospel, but it's a general notion of a mapping from a log odds ratio to how strong that effect is. This particular mapping is going to depend on the domain, so I wouldn't take it too seriously, but it's at least a step toward getting calibrated. But that's enough of that. Now, onward to part 2. Okay, so we are going to start talking about quantifying precision. This is the question I got a minute ago. I've measured effect size, and I'm going to tell you that the Cohen effect size is 2, or I'm going to tell you that the log odds ratio is 0.8, and you want to know, how good is my estimate? How much might I be off by? And that is a perfectly good question to ask. So let me start with a different problem, which is, suppose you want to know how heavy people in the United States are, and you decide to do a telephone survey. So you choose random numbers from the phone book, you dial the numbers at random, and whoever answers the phone, you ask them, how much do you weigh? And you write it down. And now we want to try to say something about the U.S. population as a whole based on that way of doing sampling. And my question for all of you is, what could go wrong with that methodology? So talk with the neighbor for a minute and see if you can enumerate all the things that could possibly go wrong with that. I don't want to interrupt your fun, but I'm going to interrupt your fun. All right, talk to me. What are some things that might be wrong with my methodology? Why is my answer going to be wrong? I hear liars. So people might not tell me the truth. Okay, that's one possibility. Yep. So people who are answering the phone in the middle of the day might not be represented in what, can you think of like some ways that they might be different? So the numbers are random. I don't necessarily know whether they're at work or at home. Okay. Yep. If I text or school, why do you think I might get different results if I text or call? Because some people might be in the phone book or not, and that might tell you something about them, whether they're in the phone book or not. Yep. Do they still make phone books? Good. Anything else? Yeah, so this is good because you're all telling me two things that are important. One of them is that the people that I get might not be representative, and you're telling me why that might change the answers that I get. Because sometimes you can have a non-representative sample, but it's still okay as long as there's no relationship between the ways that you are unrepresentative and the thing you're trying to measure. Yeah. So people might not be very accurate, maybe because they're lying or maybe just because they don't know exactly. Yep. Yes. Scale might not be calibrated. And it might be related to income, and many of the factors that we listed are related to income. And this is kind of one of the informal rules of social science, is that everything is correlated with income. Person might lie. Yep. Yep. Okay. So let me see. I put some ideas in the slides. So one of them, many of you mentioned examples of sampling bias where the sample is not representative. What that means, if the sample is representative, then every person in the population, in this case it's US adults, should have an equal probability of being in the sample. If they have different probabilities depending on what groups they belong to, then that's not a representative sample anymore. And if the thing that you're trying to measure is correlated with that group membership, then the results that you get will be biased. So that's sampling bias. But remember that there are two parts of that. There's a right level of skepticism. No skepticism is bad. Going crazy with skepticism is bad. It's almost impossible to get perfectly representative sampling. It's okay to be approximately representative as long as there's no relationship between group membership and the thing you're trying to measure. Sampling bias, some more examples. People mentioned that people who answer the phone in the middle of the day might be more likely to be unemployed. A whole lot of things that are probably related to income. So you guys mentioned several examples of that. You also mentioned examples of measurement error, uncalibrated scale. Your question is ambiguous about whether you're asking for their weight clothed or unclothed. They might not remember their weight. They might misreport. The value neutral way to talk about lying is that they misreport. You might write it down wrong. Or one of the things that I run into in survey data all the time when I grab survey data is things get miscoded. So I did a study looking at, actually the height data that we looked at came from a very large study, 300,000 respondents. One of the problems with large sample sizes is that gives you more chances to make a mistake. They had a surprising number of people in that data set who were between 60 and 62 centimeters tall. I think there's only one person in the room right now who might have stepped out who is 60 centimeters. What do you think went wrong? Why were there so many? They were talking feet and inches. I bet there are a lot of people who are 6 feet 0, 6 feet 1. Not so many people, not so many adults. Oh, it could have been 62 inches, which is 5'2". Good point. Yep. The other thing that you see a lot is that missing data will sometimes be encoded as 99 or 999. So I did one study where I looked at birth weights for babies, and the mean came out to about 13 pounds. That can't be right. It's because I had accidentally included a whole bunch of 98 and 99 pound babies. which were respectively don't know and weren't asked, or something like that. So, measurement error, lots of examples of that. Third thing, so we're talking sampling bias, that's number one. Measurement error, that's number two. Number three, random error, which is just the fact that you collected a sample rather than the whole population. And so if you only call 3 people, then it's pretty clear that you might, just by chance, get 3 heavy people or 3 light people. And your estimate might be off just because of random sampling from the population. So those are the 3 big sources of error: sampling bias, measurement error, and random error. Usually, sampling bias is hard to quantify, often because if you knew what was happening, you would fix it. So you might not know it, and even if you know it, you might not be able to measure it. Measurement error is sometimes quantifiable. There are some ways to do that. For example, if you have 2 different processes, and one of them is more accurate than the other, you can use the difference between them to estimate how imprecise 2 estimates are, 2 measurements are. So the second one can be quantified. Third one, random error, turns out to be the easiest one by far to quantify, and therefore it is the one that we spend all of our time in statistics focusing on and completely ignoring the first 2. Despite the fact that in practice, it is almost always the case that those first 2 are much more important than the third one. But the third one is easy, so we do it. That is my warning about everything that I'm about to tell you. I'm not the only one. Edward Tufte agrees with me and managed to express it in 140 characters. Random error is but one of 20 threats to learning from data. It gets disproportionate attention because it is the only threat that can be mathematically modeled. So, let's mathematically model it. Let's get back into the notebooks. If you will open up sampling.py, read through it, run the code, work on the first exercise, and stop when you get to stop here. Okay, we have a fix for the problem that we were having with the interaction. If you find this function called plot sample stats, search for that function, plot sample stats, and add this line at the end, pyplot.show. Make the show explicit. That should allow you to do the interaction. And now, if you move the slider back and forth, and update inputs. If you had that problem with interaction, give that a try. Hopefully that's okay. In the function that is called plot sample stats, add this line. I want to go over a couple of things in the notebook. One of them is the distribution of weights for adults in the US is approximately a log normal distribution, which is kind of a funny shape. We're used to things like physical measurements on people and animals. Many, many things have a Gaussian distribution, which is this nice symmetric bell curve. The log normal distribution is not symmetric. It looks like this. It has a long tail on it. So there's sort of a central tendency around 60, 65 kilograms, but then there are heavy people who are up into the 120, 160 kilogram range. Turns out there's a reason for this distribution. At birth, the distribution is pretty close to Gaussian. And then as we become adults, it becomes log normal. If you are curious, I have a footnote in my book which explains why this is true, but it's outside the scope of our current activity. So I'm going to assume temporarily that we know what this distribution is, and I'm going to come back later and undo that assumption. But for now, assuming that we know what the distribution is, we can run simulated experiments that says, what if I took a sample of 100 people and I computed their average weight? And then I took another sample of 100 people and computed their average weight. And I did that experiment over and over. How much would the results differ from one experiment to the next? So that's how we're going to quantify the precision of the estimate, which is by pretending that we did the experiment many times and seeing how different it is from one experiment to the next. Now, The thing about this example that is going to become confusing in a couple of minutes is the difference between n and iters. So n is the sample size, and that's really important. That's the number of people that I'm going to go out and measure. And what we're going to see very soon is that as the sample size gets big, my precision gets better and better. When my sample size is small, no surprise, my precision is not so good. So n is the thing that really matters. Now, to estimate how precise my estimates are, I'm going to run lots and lots of simulated experiments. And I'm calling iters is the number of times I run the experiment. That doesn't matter very much. It just needs to be reasonably big. As long as iters is big enough, I'm going to get a good description of my uncertainty. So iters, I arbitrarily choose 1,000 just because computationally it doesn't take very long, and it's big enough that I'm going to get answers that are close enough. Okay. So n is important, that's the sample size. Iters is just the number of simulated experiments that I'm going to do. So there's just taking one sample and computing one sample statistic, and now here, compute sample statistics is the function that runs lots of iterations, and I'm using a Python list comprehension there just as a syntactic way of kind of like a faster for loop. Now, this distribution is the important part of the whole thing. This is, I ran 100 experiments. No, I ran 1,000 experiments. And for each experiment, I computed the estimated mean of the adult population, and I plotted it. So one time when I ran the experiment, I got 72. And one time when I ran the experiment, I got 74. And then there was that crazy time that I got 68. And then other crazy time that I got 77. And I just plotted them all. And this is showing me how much variability there was from one experiment to the next. Okay. This thing is called the sampling distribution of the mean. It's telling me how much my estimated mean will vary each time I run a sample. The question is whether it is a normal distribution. And the answer is it is going to asymptotically become a whole lot like a normal distribution. Even though I'm drawing from a log normal distribution, it is nevertheless the case that as my sample size increases, this thing is going to look more and more like a Gaussian. Because, anyone? That is the central limit theorem that I just invoked. Now, remember what the question is that we're asking, which is I've estimated the population mean, and I've said that it's 72 and change, 72.5, let's say. Now, you ask me, how certain are you about that? One way for me to answer that question is to show you that distribution. I could show you the whole thing and just say, it's like that. I think it's probably about 72, but it might be as high as 76. It could be as low as 68, but I'm pretty sure it's somewhere in that neighborhood. That would be fine. But if you want me to boil it down to a number, there are two ways I can do that. One of them is I can compute an interval, and what I might do is like chop off the lowest 5% and the highest 5% and show you the 90% in the middle. That would be a 90% confidence interval. That's a way of taking this whole big blue distribution and boiling it down to, in that case, just two numbers. And I think I computed them here. So the confidence interval is the interval that is between the 5th and the 95th percentile. That'll be the 90% confidence interval. It is between 70 and 75 kilograms. And if you want me to give you a measure of my precision, I could instead of computing an interval, I could take the standard deviation of that thing. The standard deviation of that thing is called the standard error, and it is, loosely speaking, it's about how much I expect to be off by. So I could put this into a plus or minus. I could say, I'm going to be off by about 1.6 kilograms. So one way I could report this result is I could say, pretty sure it's about 72 plus or minus 1.6. So that would be the standard error. So standard error and confidence interval are just two ways to summarize the sampling distribution, and that is why the name of this function is summarize sampling distribution. And what it computes is the standard error and the 90% confidence interval. The other thing that I wanted to do with these results is show what the sampling distribution looks like. So when the sampling size is 100, the standard error is about 1.6, and the confidence interval is that. If I go back out, and instead of asking 100 people, I ask 1,000 people, I expect the width of this distribution to get narrower, and it does, except that it got scaled. The standard error got smaller, and the difference between the confidence interval, the width of the confidence interval, got smaller. To see that graphically, we can interact with it. So here's n equals 100. As I crank up the sample size, the sampling distribution gets narrow, the standard error gets small, and the width of the confidence interval gets small. As the sample size goes down, it's the opposite of this. Good? Questions? Yes? What does the confidence interval actually mean? Let me come back to that one in a minute. It's a great question. It's the question of the 21st century. Now, one nice thing about this framework is that we now have a way to compute sampling distributions for anything that we want to measure. So far, I've been talking about the mean adult weight, but we could use this to compute the sampling distribution of anything, like the min, or the max, or the median, or the standard deviation. So let me do that one. I'm going to copy this. Yeah. So I can take all those functions that I just used, the ones that do all of this random sampling. The only thing I'm going to replace is this function called samplestat that just says, if you give me a sample, I'm going to compute its standard deviation. So this is like, I'm going to run a bunch of experiments. For each experiment, I'm going to compute one estimate of the standard deviation, and then I'm going to plot the distribution of those estimates. And what this says is that I think that the standard deviation of adult height is about 16 kilograms, but my standard error is about 1.4, and I have a confidence interval from about 14 to about 19. And if you did the exercise, did you try this out with a couple of different statistics, we can compute a confidence interval for anything that you want to measure using this framework without making any changes. And I point this out partly because if you try to do the same thing mathematically, it gets really hard really fast. Computing the sampling distribution of the mean, easy. Standard deviation, harder. Median, quite hard. Interquartile range, very hard. Whereas computationally, we don't care. If you can compute it, I can tell you the confidence interval. Questions? Okay, let me just summarize a couple things there, and then we'll get back into the workbook. So one of them is we are trying to quantify the precision of our measurements by running lots of simulated experiments. What we get is a sampling distribution, and we summarize the sampling distribution using either SE, which is standard error, or CI, which is confidence interval. Mentioned that? Okay, but here's where I now have to undo the assumption. Remember at the beginning I said I'm going to assume that we know the actual distribution of adult heights, and now we're going to go through this elaborate process to try to compute the mean. Well, if we knew the actual distribution, we wouldn't need a process, we would just compute the mean. So we have to do something else, which is if we don't actually know about the population yet, all I have is a sample. How do I run simulated experiments just based on my sample? And the answer is I'm going to take the actual sample that I measured, and I'm going to use it to build a model of the population. It won't be perfect, but it's a model. And I'm going to use the model to simulate more experiments. There are a lot of different ways to do that. One of them is resampling. And in particular, resampling refers to a lot of different techniques. The one particularly that we're going to do is called a bootstrap, which is that we're going to pretend that the sample that we collected is the entire population. It's kind of a funny move to make, but it almost makes sense. And then I'm going to draw new samples from the actual sample with replacement. So let's see what that looks like. Code, let's go back to sampling.ipynb and move on to the next section. Read about it, run the code, and we'll debrief. So we're getting into object-oriented programming here in Python. If you're familiar with that, writing a new class that extends an existing class, that might be familiar to you. If it is, fine. If it's not, this might be a good chance to switch over to using the sampling solution notebook, which has a solution in it, or you can take a look up there where I've conveniently provided a solution. Okay, I want to debrief a little bit about what's going on here, and then we'll get into the code just a little bit. The fundamental idea of this way of doing resampling is that we're going to take the actual data that we collected and build a model of the population, use the model to generate fake data, and then compute whatever the statistic is that we're trying to measure, and then we're going to report either a standard error or a confidence interval. This framework is my attempt to explain resampling in one slide. So this is across the top row there is the actual data and the actual estimate. So in this case, I've collected a bunch of adult weights, and I've computed their mean. So sample statistic in this example is the mean, and the estimate that I get is 72 kilograms. So if you ask me, what's your best guess? What's your best estimate? That's my answer, the top row. Now if you ask me, how sure are you? That's where the bottom row comes in, which is that I'm going to use the data to make a model, and that's where this resampling from the data comes from. Generate lots and lots of simulated data. In this case, it's just 3. In the code, it's 1,000, but I didn't want to draw 1,000 of them. And again, whatever the sampling statistic is, you compute that for each fake data set and collect the distribution of them. And what you get down there in the lower right-hand side, that is called the sampling distribution of the sample statistic. In the example that we're doing, it's the sampling distribution of the mean. And whatever that distribution is, that's one way to describe how confident you are about what you measured. But if somebody wants a summary, you can give them either the standard error, which is the standard deviation of that thing, or a confidence interval, which is usually the gap between some low percentile and some high percentile. Yes? Yep. That's a great question, and let me paraphrase in case people didn't hear you, which is that the arrow there, when you go from the data to the model of the population, it seems crazy that these data sets have the same size as your original data set, because it seems like you're using your data over and over. It seems like you should divide it up into small pieces. And if you're coming from like machine learning and you're thinking in terms of making a training set and a test set, I understand that intuition. Nevertheless, it is the correct thing to do that these fake data sets have the same size as the original. And part of it is, again, because sample size is going to tell us how uncertain we should be. Yep. Yes, if you sampled without replacement, then you would get the same data set over and over. But when you sample with replacement, what's going to happen is, let's say you've got 100 people, in any given resample, some of them will appear more than once, and some of them might be left out altogether, and that's how you're going to get some variability. Good. But your intuition is exactly right. That's what people find funny about this. It is actually okay. Up to a point. If your original sample size is kind of small, you're not going to have a lot of variation in it. You're not going to see the full range of possible values. And no amount of resampling is going to magically make new values appear. And that's why I'm emphasizing that this is a model. When you go from the data to the resampling process, you are making modeling decisions. One of the things that you could do is smooth things out. So if you measure 10 people and you find that somebody is 6'0" and somebody else is 6'2", does that mean that there's nobody in the world who's 6'1"? No. You could reasonably guess that there are probably people smoothly in between the people that you actually measured. So you could, instead of just resampling, you could take your actual data, smooth it, like fit a statistical model to it, and then draw samples from that model. And that would be a totally reasonable alternative to what I'm doing. Would that get sketchy if you're on the far ends? You're going to have to make modeling decisions, and you're going to use your domain knowledge to guide those decisions. So if you know, look, there are no people in the world who are 11 feet tall. So if my model says that there are, that's a problem. But yeah, when you are making modeling decisions, there is a certain amount of arbitrariness to it that you can either pretend it's not there or embrace it. And I'm in the embracing school. Not so much with people, but with data. So is this a weakness in this strategy, which is that you have to develop a model? There's no alternative. The analytic results are also based on models. It's just that they don't make the models explicit. So I think it's actually a virtue of this that it forces you to think about your modeling decisions. Yeah. Yeah, you're right, and maybe I didn't make it as explicit as I just promised. But it is implicit in saying that I'm taking my sample and I'm pretending that the entire population is represented in my sample. So now when I want to simulate an experiment and generate a new sample, I'm generating it from this hypothetical population. And it was that move when I went from my sample to pretending that it's in the entire population. That was the modeling move. If instead I took my sample and I replaced it with a smooth analytic distribution, that would be a different model. And provided that I have a reasonable sample size and that I don't make crazy modeling decisions, it will all turn out okay. All the different methods will give results that are pretty close to each other. Yes. I would say that your initial sample plus your resampling process, I would draw a dotted line around those two things and say that's the model. It might be helpful to do the diagram. So what I'm calling Model 1 there is conventional bootstrap resampling. I'm just taking my original data and I'm doing sampling with replacement from my data directly. An alternative is you could take your data build a smooth analytic distribution that fits your data, and then draw random samples from the smooth analytic distribution. Both valid methodologies, again, probably consistent with each other for reasonable assumptions. Yeah? The quality of your random number generator is not going to be a big factor here, but the